Good morning, everyone. Happy Monday morning.
Good morning.
Yeah. So welcome to the 16th annual HPC-AI Swiss Conference. This is probably our second year where we've put on an AI spin. I think with the feedback that we received last year that more AI would be good, and so we did. So I think in the agenda that you're going to see over the next 3 days, you'll see a lot more AI-focused sessions, which is great because AI is starting to influence HPC and scientific computing, as we know.
So from my side, good morning, everybody. It's really great pleasure to see all of you here again in Lugano. I mean, it's really 16 years of HPC advisor in Switzerland, and I think it's still getting in. We have great talks this year. I believe 3 days, 3 intensive days. I believe it's going to be a pleasure, whatever. I mean, what the reason for you here, it's great, like, you know, different reasons. It's good that we can focus on this share of knowledge, collaboration, and let's make it great event.
This is Hussein Harake, by the way, from CSCS.
Yeah, exactly.
Probably should have introduced ourselves. And I'm Brian Sparks from the HPC-AI Advisory Council. We couldn't have done this, of course, without our sponsors, and we have a great number of sponsors that showed up this year, probably about 20% more than last year. So we're seeing growth there, and it's great because as the attendees grow, so do our needs, and it gives the sponsors a great chance to be able to speak with you all. So the only thing that we request is during the extended breaks that we've added in the agenda this year, as well as lunch, just go visit their booths. They're going to be right behind you there with all the food and everything else. So they're ready to talk with you, and just say hi. What else? So we have the agenda. So you probably have a pamphlet for just today. We don't want to get you too ahead of yourselves. So we'll probably pass out day 2 tomorrow and day 3 the third day. Surprised we didn't give you all 3, but hey. Here it is. You can always go to the website, hpcadvisorycouncil.com, and there you go to the Swiss conference, and that'll be the agenda. One of the things that we'll do after the conference is post all the slides, and of course, Dan Olds is here videotaping everything, so we'll have all the video sessions available as well. So give that a week or 2 to be posted online, and it'll be great.
So if you believe that this is not enough per day presentations, I mean, you know, you could always add, but I believe that hopefully that's quite intensive. And there are like different talks that for the first time at the HPC Advisory, and different important professors in the HPC community are coming and just share their knowledge, and that's really very interesting for us.
Yeah, I think we have 30 sessions in all.
Okay, so we agreed that we would like to promote a couple of events taking place this year in 2025. And you know, we started by dates. We have three actually events taking place. One of them is an important one for the research and the HPC community, and it's a past conference that's taking place in the area of Zurich called Brugg, and that's from 16 to 18 of June. It is really one of the most advanced scientific events in Switzerland. It's managed by CSCS in collaboration with ACM. So if you have any publication, that's a place to go. Okay. And the second one, this is summer school. It's going to be here in Lugano area, and this is, I believe, it's more important for students when they are starting and also getting some credits for it. So that's also a good start working in programming accelerators, and I believe that's an important step for students. Even for mentors, they would like to join and help. And that's going to be in July. It's in full summer of Ticino, and I believe that's like an important step for us. And the last one is going to be the Harake. Harake is you know, organized by Open Hackathon collaboration with CSCS, this time EPFL and Swiss AI. And here, just importing codes. So if you have a code, you would like to optimize it, you would like to, you know, bring it to accelerators, this is the place to go. So you can also join there.
All right, so I want to just give you a brief overview of the HPC Advisory Council. After all these years, I'm pretty sure you're fairly familiar with it, but just for posterity's sake. So we've been around for quite a while. We have about 450 active members across companies, universities, major research institutions. Our goal is to basically provide as much information as possible freely and I guess in an open source kind of model. We explore a lot of different future technologies too, and we do this through various mechanisms like the Council Cluster Center. So this is a center that we have about 8, now it says 6. So we have 6 clusters. We had almost 12 at one point, but we just moved to a new data center, which of course impacted our work a little bit last year. But now we have a couple Grace systems. We do have some H100 GPUs. We don't have any B200 or anything like that yet. But we mostly have the Intel and AMD CPUs. We have some storage. These clusters are available free of charge in terms of accessing it, so you can, if you want to test your code, if you want to see what it runs on those particular systems, those types of environments, that's great. The Grace system is a very interesting system that we're seeing a lot of activity on. So it's one of those things that you want to jump on if you want to take a look. We have 10 best practices that were added last year despite the downtime, which is fairly decent. We have the majority of the HPC software already with some application best practices, some performance metrics. We kind of go over all these different applications every year, just with some of the latest hardware, so we can see the latest and greatest in terms of the specs and the various runtimes. And one of the other things that we do is work actively with students. So we have the ISC Student Cluster Competition that we hold each year. We probably have some previous students from that, from the CSCS ETH team. They'll be there again this coming year. We've expanded it to now 10 teams worldwide, and we have about 25 that participate in our online version of it. And we have RDMA programming in China. We have other APAC student activities too, so we're working with students from around the world and trying to get them up to speed and get their skill set up.
If you allow me, one word about the HPC advisor, since I deal with students, and this is really an activity that I process that I really love and handle it. When we get students, for first year at ETH, from computer science or computational science, we are talking about students, they have really little knowledge about even Linux itself. And after 6 months or 1 year from working on the HPC advisory, we have experts in optimizing and really scaling codes, scientific codes on our clusters. And this is really impressive. And plus, there are a lot of ideas comes from these students. So it's one of the most brilliant activities that we are just handling it with the students and getting at the end of it just really experts in this field, which is we always need.
Yeah, thank you. Yeah, it's quite a long process for the students. So they're engaged for quite a few months with a lot of extensive training that we provide from different open source software developers that they'll come on and they'll train them on the software. So there's a lot of advanced training that we do beforehand to the students to be able to give them as much information as possible for them to be successful. Apart from this conference, we do another conference, usually in Singapore. It kind of changes now because this is in collaboration with HPC Asia. So I think next year I'll be in Japan. Same with Swiss conference. Here in spring, we also hold our Japan conference. I think it's going to happen next week, but it's going to be virtual only. And summer, we take a little bit of vacation, hopefully. And then we start again in autumn with the UK conference and China conference. So we participate with DRAC every year in October. And I think that's it. So very happy that you're all here with us. 3 days of exciting content.
Okay, so it's a great honor and a great pleasure for the first time from the past conference to the HPC advisory. I mean, a professor from the ETH, from the Computational Applied Mathematical Laboratory at ETH, just joined us this year to give us our opening keynote. Really, if I have to start presenting all achievement, that will take us 15 minutes. So Sid from ETH, just really great honor to see you here. Please welcome, join us to welcome.
I'm actually 10 minutes ahead of schedule, but we don't do that in Zurich, right? Okay, so without further jokes, so first of all, thank you very much, Hussein and Brian, for inviting me to this beautiful venue. Lugano is one of my favorite cities on earth, and I always enjoy any opportunity to come here. So let me jump right in. How does it work? Oh, the other way around. Yeah. So I have a very grandiose title, AI for Physics, but my presentation is much more focused, right? So this was just to elicit some interest. Okay, so let me jump right in. So since we are going to talk a lot about physics today, let me start with some examples, some use cases. And we're not far from the Mediterranean, right? It's a few hours by train to reach the Mediterranean. And just imagine that there is an earthquake. Hopefully it doesn't happen, but it has happened in the past and it's bound to happen in the future. Just imagine that you have an earthquake which takes place off the coast of Crete. Because it's an earthquake, particularly a powerful one, a lot of water is going to be displaced, and that is going to set off tsunami waves, right? So this is the mechanism by which tsunamis are generated. Now, what happens is that these tsunamis are going to be generated, they're going to spread all over the Mediterranean basin, and we need to be warned in advance about evacuation, for instance, right? And the responsibility for that is taken up by this agency here. It's the Italian Institute of Oceanography, Volcanology, and Geophysics, which is based out of Napoli. And what they are going to do is, as soon as an earthquake happens, and there is some indication of how much of, what's the strength of the earthquake, what's the location of the earthquake, and so on, they are going to, or they have to predict what is called the wave height and arrival time. So this is just a waveform. So you can see that as a function of time, what is the height of the wave, but at buoys. And these buoys are just off the coast, all along the Mediterranean. I've just picked two of them, one off the coast of Greece, and the other is off the boot of Italy, right? So in each of these buoys, they look at these waveforms, and then they're going to issue tsunami warnings. The problem is that, so this is the way it has to be done, and by law, by European law, they are sort of mandated to do this, right? And this has to be done in real time. So this is as soon as the earthquake happens, and they have to do this prediction. And so this is an example that comes from, let's say, from the public sector that we are sort of interested in. Another example, and this also has an Italian flavor. I chose it because we are not far from Italy. So this is with race car design. All of us want to drive a race car, if possible. Probably very few of us have the opportunity. So these race cars are designed by, some of them at least, are designed by a company called Dallara, which is based out of northern Italy. And the way they do it is, so this is a sort of a model of a car, and at the end of the day, they have to test some prototypes in a wind tunnel, and then decide on which is the best model, right? And to do so, what they have to do is they have to sort of design it. There is a big design configuration. There are many, many different parameters that need to be sort of explored at least. And they don't want to put every single shape that comes out into the wind tunnel, right? They want to sort of design it in silico and then take it to a wind tunnel. And this requires that for a given car shape, based on different parameters, they want to predict aerodynamic body forces, lift, drag, and so on. And they want to do this at scale so that the design process can be accelerated. So this was an example of the kind of stuff that we do, which comes more from an industrial application rather than from a public sector application. Now, the question is, how are these problems solved, right? And many of you work on HPC, and you probably have a good idea of how these problems are solved. There's a pipeline, and the first step of the pipeline is that you have to have a mathematical model, right? And the mathematical model, and this is where the physics comes in, because whether it's tsunamis or flow past a car or an earthquake or whatever you think of, it's essentially the laws of physics that are at work. And we know that these laws of physics, they are embedded or they are codified in terms of mathematical objects called partial differential equations or PDEs. I think all of you saw some of it during your university studies. Now, PDEs essentially are the language of nature, just like we have natural language to express human thoughts, emotions, human knowledge. Natural knowledge in some sense, physical knowledge is expressed by PDEs, so there is a strong sort of a language component there. The other thing is that PDEs, they are all over the place, right? So even if you start from the smallest subatomic particle, just imagine the motion of a single electron. This is governed by the Schrodinger's equation, PDE, and all the way to sort of galactic, cosmic scales. For instance, when two binary black holes sort of collide and they're going to let off gravitational waves, you have to model this by the Einstein equations, by certain particular solutions of the Einstein equations. So all the way from the smallest to the largest scales, nature is described by PDEs, including human scale, like in weather and climate, or flow past a vehicle, or, I don't know, compression of a beam, things like that, right? So this is the first thing, that they are very, very descriptive. The second thing, which is very important, is that there's a huge amount of diversity. As you can imagine, things change, right? So for instance, how sound propagates in this room is very different from how a fire is going to propagate in this room. So there's enormous diversity in physics. All of this is somehow codified in terms of an enormous diversity in PDEs. And finally, which is, of course, already indicated here, is that there is massive sort of variation in scales, right? So you can imagine in space, you're all the way from 10 to the minus 20 to 10 to the 20. Means it's an enormous range of scales. Similarly in time. So this is rather comprehensive. So that's the first set. So you need to describe your natural phenomena that you're interested in, your physical phenomena, in terms of these PDEs. But that's not enough, because the problem is, and all of you know this from basic math, that just because we have an equation doesn't mean we can solve it. So it's not possible to find sort of write down formulas. Maybe in some simple cases we can do that, but in general we can't do that. And this is where numerical algorithms come in, which are also some of the early motivations for computing in general, and certainly for HPC. And you have all this variety of type of algorithms. You find differences, find volumes, find elements, spectral methods, lattice Boltzmann, right? And in fact, Brian showed you all these benchmarks, these HPC benchmarks, and many of them are based on these kind of algorithms. So that's a good thing. And these algorithms are extremely successful, including some applications in my lab, where we do everything from the core collapse of supernovas to sort of propagation of waves in the sun. All of these are done on HPC architecture provided by CSCS, simulation of clouds, stratocumulus clouds, flow past rockets, simulation of tsunamis, and so on. So this is an extremely successful and mature field, and there are many, many highlights. Some of it I'm sure you're going to see today and tomorrow and day after. So the examples that I spoke about, the use cases as it were, so for instance, tsunami simulation is done with what are called the shallow water equations. I'm not going to write down the equations here, but shallow water equations, which tell you nonlinear wave propagation on shallow surfaces. For instance, the ocean is shallow compared to how long it is. And you can see that when you solve it, you have all these tsunami waves that are propagating, and they're reaching various places in time. Similarly, if you want to solve flow past a car, you use Navier-Stokes, possibly with some turbulence model, and you get, for instance, a pressure field which looks something like that. And all of this can be done with different kinds of numerical methods. However, what's the catch then, right? And this is the important thing here, is that there are some issues with these traditional numerical methods. The first one, of course, is cost, which many of you try to sort of solve in some sense. And just to sort of give you some numbers, some scale of the cost, let's look at some concrete examples, just from my own research, but you can scale it to your use cases. So here is a very simple example. There's a solution of the Navier-Stokes equations in 3D on a periodic domain, so as simple as it gets. But the initial conditions are something like this. So this is shear across a cylinder, and as you propagate in time, you get a very, very complex solution. So there's a vorticity of the field, the vorticity intensity of the fluid flow, and you can see that there are all these whirls and eddies and so on and so forth. And this is a very complex solution, can be solved, means this is not an issue. We can do that at scales, 1024 cubed, so approximately 1 billion degrees of freedom per time step, roughly speaking a little more than that, 3-4 billion degrees of freedom per time step. And this, for instance, we have a very optimized spectral methods code that can do this at scale. And just to give you some numbers, so this is DANT. This was the previous big CSCS machine that we had access to. And if you had used the CPU partition, this would have been approximately 4,500 CPU hours for a single simulation, right? This is not a very complex problem. It's periodic box, Navier-Stokes. You have an optimized code, 4,500 CPU hours. What saved us, of course, are GPUs. We were able to scale the code on GPUs with some help from CSCS, and then this cost dropped to about 100 GPU hours, which is okay. It's 100 GPU hours, you can certainly afford it, right? A speed up of approximately 50, which is great in this particular case. But the catch is that this is not good enough, because this particular realization of the flow is of no consequence whatsoever. Why is that? This is a chaotic system. You make tiny, tiny little perturbations. I don't know if you can even see this, but these are really, really tiny perturbations in the initial conditions. Then you can see here that the flow changes entirely. You see, this guy here is completely different from this and this. Qualitatively, perhaps they're similar, but quantitatively, not at all, right? So this is chaos. So this is the problem here. So you can't just do one simulation. You have to do multiple simulations, what is called uncertainty quantification, and then these have to be, they can be done in parallel, but they still have to be done. And this is costly, right? So at least on date, for a single uncertainty quantification simulation of the fluid flow at this resolution, this would have been 100,000 node hours, right? And we did get some grants to do this 100,000 node hours, but just for one particular problem. Now, if I do 5 problems, my entire grant is over. And this is from a single academic lab. Now you can scale it in the domain that you're looking for. So huge advance in HPC, which even makes this conceivable to these kind of simulations, but at the same time, it's still expensive, right? Then you tell me, okay, things have changed, our machines have gotten better, so just in practice, we have access to ALPS now, which is, I think there are some presentations on ALPS later today by Dr. Fauzi, and ALPS is, of course, a Grace Hopper system. It's a very powerful system, and the simulation cost does drop. So remember that earlier, sorry, I just have to go back, not forward. Earlier, we were at something like 100 GPU hours per simulation, and now this is like 25. So at least at this scale, it drops by a factor of 4. It's still a big simulation, right? But this is, just imagine doing this 100,000 times. It's quite expensive. Sorry. I'm still getting a hang of the system here. But no worries. So this is still quite expensive. So my point is that whatever be the application and whatever be the advances that we're making in HPC, there is going to be still a big discrepancy between where we are and where we need to be. So I forgot to add a slide about this, but let me go back to the use cases, right? So this guy here, the shallow water equations, later on you'll see it. This is an optimized GPU code, which is even operational to some extent, and this still takes approximately 1 hour. 1 hour, it's 2D, so 1 hour is good. But however, remember that 1 hour is when these waves have already reached these places, right? So this is exactly the simulation. This is the actual physical propagation at 1 hour. So you can't do it at 1 hour. You have to do it in 1 second so that you can issue the warnings. That's why the system is still not real time in some sense, right? And similarly, this simulation, this is on a very complex geometry, complex mesh. It's not yet on GPUs, so it's very difficult to optimize it. And then this takes forever. So this was 500 node hours for a single shape. And just imagine if you have to do this 100,000 times or 1,000 times, this becomes very, very difficult. The bottom line is that despite all the advances that we have made with HPC, solving PDEs, or in other words, simulating physical reality, is still quite expensive. Perhaps this can be solved one day when we have faster systems, but the second problem will always remain, and this is sometimes called the sim-to-real gap, but it's essentially that we don't know the physics. So remember, my pipeline is, I have some phenomena, I have a mathematical model in the form of a PDE, then I solve it, then I go to my big HPC system and get throughput, right? So this is roughly the idea. But now what happens is, what if the first step itself, you have a hurdle there, you fail there? And this is not untypical. Let me give you a concrete example. So just imagine the Earth system. There will be talks about this, presumably, at the conference. So the Earth system, we all know that the flows in the atmosphere and the ocean, these are Navier-Stokes with some additional terms, but it's essentially Navier-Stokes and the laws of thermodynamics. Radiative transfer is radiative transfer equation or radiative transport equation. Those are well established, right? However, this is not all the things that are there in the Earth system. We have vegetation, we have soil, we have land, and various other sort of ingredients where it's very difficult to sit and write down formulas, first principle formulas, and derive a set of equations, right? So then what people do is that they often parameterize them, model them, fit parameters, and so on, but there is no definite knowledge of the equation of the underlying physics that is there. And this is true for subsurface flows, it's true for biological flows. Traffic, for instance, is another example. This is a picture from the, I don't see you if you see it well, but this is a traffic simulation over the city of Zurich. And in all the cases, all that I'm trying to say is when you go to the real world, when you have to combine different parts of physics, there's a gap here. That when you do simulation on what you observe in reality, there is going to be a gap. And this is not going to be met even if you have faster machines, right, with this particular pipeline. However, in both cases, either if the PDEs are too slow to solve, or if you don't even know them, we still have data, right? So for the Earth system, we have enormous amounts of data, but all these applications, we have some data that is lying around. So the paradigm that has been changing in the last, let's say, 5 to 7 years, also in the theme of this conference, as Brian said in the last couple of years, is what about sort of making use of this data, leveraging it together with the physics, and then trying to learn or solve the PDEs with some data, right? So this is sort of the basic paradigm that I want to present here. I don't want to sort of go into details and technicalities, but just to give you a little bit of flavor of some of the underlying math so that you don't get, it's not just superficial. And the idea is very simple. So at the end of the day, I have PDEs. Some simple ones are written down here. This is what is called the diffusion equation, Darcy flow, heat conduction equation, stationary diffusion, and so on. So you can think of a PDE as a system, right? Or physics itself as a system. And what you do is for the system, you provide some inputs. So in this particular case, this is going to be the coefficient. Or for instance, for the propagation of sound, it could be the initial conditions or the material properties of the medium that sound is propagating in. So these are going to be the inputs. And the output is going to be your solution itself. So the intensity or sound pressure at different points or different kinds of observables. So think of the PDE or the physical system itself as a system which takes in some inputs. There's something here, this is the initial condition, this is the final solution, and so on. And then it provides you an output, which is the solution. So the operator is the object that formalizes this notion. It takes in this input, right? Just imagine weather today and provides an output, the weather tomorrow, the state of the weather, the mathematical description of the weather tomorrow. And the point is that these operators essentially are infinite dimensional. Why is that? Because mathematical functions are infinite dimensional, right? That's what distinguishes them from vectors. You can, in principle, measure sound or temperature, sound pressure that is, or temperature at any point in this room. So this is the reason why these are functions. So essentially, you have an infinite dimensional object, and the task of learning is to learn this infinite dimensional object, this mapping between infinite dimensional objects from data. And this data is given in terms of some data distributions. You have some samples, some noise, and so on. And at the end of the day, you have to find some approximation to this operator. So this is the task. Just imagine for simplicity that you have several states of weather, and the task is to predict the weather tomorrow or something like that. That's a typical example, right? But the important thing is that in principle, this is an infinite dimensional problem because you can measure things everywhere. But so how are we going to solve it? So this is where we use AI, of course, these days. And we know that the three sort of pillars of AI are, first of all, we have more compute, GPUs, huge amounts of data, which is true for many physics applications, not true for many other physics applications, as you'll see. And finally, these incredible mathematical objects, deep neural networks, which allow us to process the data. And I think all of you know that what neural networks or deep neural networks do, whatever be their nature, whether it's an MLP, CNN, transformer, what they do is essentially they take a vector input, right? Maybe a very, very big vector like an image, which is, let's say, a million dimensional vector, and they provide an output, which could also be another million dimensional vector. But all of them are finite dimensional, right? But what I showed you in the last slide was that the objects that I am interested in, these are intrinsically infinite dimensional. So there is a mismatch here, that I have something which is finite dimensional in practice, and something in principle is infinite dimensional. So there's a dichotomy, and a lot of work needs to be done or has been done in order to sort of clear this dichotomy. And what I'll present here very quickly is just a basic formalism on how this dichotomy can be cleared. So what you do is, this is one way, but there are many different ways, is that instead of working with finite dimensions, in principle, why don't we extend neural networks to infinite dimensions? And this can be done on paper, that's not a problem. Remember that neural networks at the end of the day are mathematical objects. So given a vector, you multiply a vector with a matrix, add another vector. So this is what is called a weight matrix, right? All of us know this. This is called a bias vector. And then you apply a nonlinearity, pointwise, ReLU or something like that, and hyperbolic tangent. And this is done for every component. So this is the basic construction of a neural network. Now the difference that we have is that instead of having a vector input, we have a function or a field input. Just imagine the initial distribution of temperature over Lugano, right? So this is a field. So how can we generalize this? It's very simple in some sense, right? So instead of having bias as a vector, you just write it as a function. So the dependence on x tells us that it can vary over space, for instance. And the key point is here. So you have a matrix vector multiply, and we have to sort of generalize that, extend that to infinite dimensions. And this is sort of function analysis 101. The extension is these kind of kernel integral operators. So the best way to think of it is if you discretize this object, you'll get a matrix vector multiply. So when you extend it, you get a kernel integral operator. So you have a kernel, you throw it on the function and integrate these objects. And then here you keep the same structure. The nonlinearity is local and is applied at every point. And this leads to what are called neural operators, which are infinite dimensional objects. Of course, in practice, so and in principle, they can get infinite dimensional inputs and provide infinite dimensional outputs. No problem on paper, right? Of course, in practice, they have to be discretized because we can never compute this integral by hand, and we can never do the computations by hand. We have to do it on a computer. And that's why we say that we first learn and then we discretize. So that's sort of the idea here. The problem is that this is computationally complex simply because, as you can imagine here, this integral is going to be quadratic, right? Because there are 2 points per every point here, so it's quadratic in the number of points, which is quite a bit. So you have to choose the kernel smartly, and there are many, many choices available. So for instance, something called Fourier neural operators, which use the FFT essentially to do this fast, right? So what is happening here is that the kernel, as you can see, this is translation invariant. A lot of physics is translation invariant. Things don't change if you move the frame. Then you put a translation invariant kernel, and then this operator becomes a convolution, and convolutions can be fast, computed fast in Fourier space. So what you do is that you start with an input, take a Fourier transform, convolution becomes a multiplication. So this is a learnable matrix. Then you take an inverse Fourier. This is not my work. This is from some people in Caltech. You take an inverse Fourier transform, and then you apply the nonlinearity. So this is still non-local convolutions. You're doing convolutions. Machine learning is a lot about convolutions. So you take a non-local convolution in Fourier space, and you take some local activation, nonlinearity here. And the main point here is FFT, right? The most effective high-performance computing algorithm that you can imagine. And that's why it's efficient, it's very widely used, and it's backed by solid theory. But that's not the only thing that you can do. So you have some infinite dimensional object, which you discretize in finite dimensions, and this is what you get. What we did is to keep the same scheme, but instead of using, again, I'm sort of confused about this. So instead of using non-local convolutions and local activations, what we did is we stick to local convolutions so that we don't do it in Fourier space. We do it in physical space, but the kernel itself is going to be rather narrow-banded. So as long as this is not a full kernel, it's a narrow-banded kernel, you're still computationally quite efficient, and it is computationally quite efficient. But what we need to do is to change, we have to bring in some non-locality, and that is done through the activations, which are sort of locally spread out. There are some details here. And at the end of the day, you end up with some kind of a UNet or an operator UNet, where the data that you have is split into different resolutions, high resolution, low resolution, and then it's going to be processed. Details are not important here. The point that I'm trying to say is that you have to change slightly the sort of standard machine learning that one uses in order to deal with this essentially infinite dimensional problem. These are two different ways to do that, and these work very well in practice. So just just to start with, some very simple examples in 2D on a periodic. You don't need HPC for this. My GPU is good enough. The GPU on my laptop is good enough. So what you do is that you have some inputs here, Navier-Stokes equations again, and this is the output. So this is the initial velocity, this is the velocity at a later time, initial vorticity, vorticity at a later time. So you can see all that the flow does is that it rolls up these vortices which move around and combine. It's a fairly simple flow. And then when you test these things, you see that they are quite reasonable. For instance, you get 3% error with a few samples, 1,000 samples approximately. But the main difference between the architectures here is that, remember, that this is an infinite dimensional object. So essentially, you can sample them at different grid resolutions. And when you do that, when you test on different grid, you train on a certain resolution. And when you test on different grid resolutions, for instance, FNO does not generalize very well to new resolutions because machine learning is all about generalization. CNO, our architecture, it generalizes seamlessly because by design, it has this design principle that whether you learn and discretize, like what I showed you, or we could have discretized first, projected our problem into finite dimensions, then done some neural networks on top of that. So these two things commute. They are exactly the same. For those who know optimization, this is like optimize, discretize, and discretize, optimize, and these things have to be the same. And then you see these nice properties. But the bottom line is that on the simple problem, things mostly work, right? And this is true for a lot of benchmarks. In the paper, we have different kinds of equations, Poisson equation, wave equation, Navier-Stokes, Euler equations, Darcy flow, and so on. These problems are quite effective. But this is not the only thing. These days, whenever you give a talk, people say, why don't you use transformers, right? Why are you sort of sticking to just the basic sort of convolutional-based neural networks, machine learning? You can use transformers. There's no issue. For those who don't know this, transformers in this setting are, remember that the kernels that I gave you before, the kernels that I gave you before were sort of this form. And this was the thing that I was sort of discretizing before. And this is a linear kernel, data dependent, but linear. Both for FNO and CNO, whether we do the convolution in physical space or Fourier space, it's still a kernel, but linear kernel. But what you could do is you can extend it. You can make this kernel nonlinear. And transformers, so the main mechanism behind them is an operation called attention, is exactly having this nonlinear. It's a particular realization of a nonlinear kernel, very easy to explain. So imagine that this is my domain, and at every point I want to update the solution or the feature, whatever you think of. Then what I do is I collect information from the neighboring points, or perhaps from all the points, and for a linear kernel, I weigh them based on the weight of the kernel. For a nonlinear kernel, I have to do another all-to-one operation, for instance, from this point, and I compute the weights by some sort of correlations. So these are essentially point-wise correlations, and they give me, let's say, a weighting, what this point, for instance, contributes to the update from this point to this particular point. So essentially, there are two all-to-one calls, and because there are two all-to-one calls, the computational cost is bound to be quadratic in the number of points or in the number of tokens, if you want to imagine in the language of language processing. And this is okay for languages. I think later on, Emmanuel is going to talk about how this is done for an LLM. But for our inputs, these are in 2D and 3D, these are fields, this is just infeasible. We have to come up with a solution, otherwise the computational complexity blows up. And the solution is already there in some sense from the vision domain, from computer vision, and these are based on what are called vision transformers. What you do is that instead of processing or attending on pixel-wise information, what we do is we divide our domain into blocks, or what are called patches or cells. For those who are familiar with finite volume methods, these are cells, and all these, let's say, information is compressed into some sort of a learned cell average. So you can think of cell averages as being your features, and these are being attended to. But of course, this doesn't scale very well because these patches or cells have to be large enough, but we can't do that. So there is another idea which is a brilliant way to sort of realize transformers in this setting, which is to use what are called windowed attention. So the idea is that there are two levels of discretization. Those who know multi-level methods, this is probably very familiar. So you have these white boxes, these are the so-called patches, and you have these big black boxes, which are sort of encompassing them. These are called windows, and you only attend to boxes, these white patches inside each window. So for instance, this guy and this guy have a correlation, but you don't necessarily go across these patches, right? So the advantage of that is that you have very nice scalability, because everything depends on just the size of the window or the number of windows that you have. So this is an estimate on the complexity. But the problem is, before I had some sort of global information processing, things were affecting each other. Now there is no direct mechanism by which points here are going to affect, or features here are going to affect the feature there. So what do you do? And this is where people in computer vision came up with a brilliant idea that, remember, that neural networks are just stacking on top of each other. So you have lots of different stacks. And then what you do is that when you have a different layer, just shift the window. So just imagine that in one layer, you have this kind of a data construction. In the next layer, you're just going to shift the window. And these 2 points which are not communicating with each other, they start communicating with each other. And then you keep on doing it, and you keep on doing it, and so on. The advantage is that you have scalability, because at any given layer, you're just attending inside a window. And the second advantage is now you have global information processing, because you're shifting the window. So what we could do is, of course, we had to modify it a little bit to our setting, which we did. And this is what is called a scalable operator transformer. So it's a transformer to this physics domain, let's say. It has the same kind of UNet multi-scale structure, but each of the underlying blocks are somehow this particular vision transformers, so-called SWIN transformers. And in fact, one could even mathematically show that for any operator, including solution operators of PDEs, these guys can approximate them, because they have these beautiful expressivity properties. So that's good. They also work, but they're no better than FNO or CNO. So whether you use a linear kernel or a nonlinear kernel, for these kind of problems, the sort of the error distribution, how accurate they are, how performant they are, is very, very similar. So there's not going to be a big issue. So if you have two-dimensional problems on a Cartesian grid, you have very, very good solutions, right? But now you know what the caveats are going to be, because nature is not Cartesian, means this is what we were able to solve till now, that you have Cartesian domains and inputs and outputs on Cartesian domains, and I showed you different ways to solve it. But just imagine that if I change the domain, still in 2D, if I have something like an airfoil, then the point distribution is going to be very, very different. The inputs and outputs are going to be very, very different, and you cannot do that anymore. So you have to look at data on arbitrary domains, complex domains, like the body of a race car, right? And then what you need to do is to deal with data coming from essentially point clouds. And this can also be done. Machine learning is very powerful these days. And there are different ways to do it. Again, I'm not going to go into details because I'll be soon out of my time. And you can use graphs. Graphs are a very powerful way to do it. Or you can use transformers. Means both options are there. They're equally good at scaling and so on. So here are a couple of papers from my lab. I'm not giving the details here. And then you can see already that for complex domains, so this is airfoil or something which resembles an airfoil. This is flow past a cylinder, high-speed flow. You can see the shock waves here. You can approximate these things very, very well, right? By the way, how much of time do I have so that I know how to modulate? Because I started at a different time and I have 30 minutes. Okay, good. Perfect. So the point is that, again, if you have unstructured grids, this can also be handled. And the last point here, sorry, again, I'm sort of making a mistake, is, so what about 3D? And so far, I have showed you examples in 2D, even on very complex grids. So what about 3D? So I can slow down a little bit and describe to you. And it's not just about the scale, right? It's also about the complexity of the physics that goes in. Again, I come back to my best friend, fluid flows, Navier-Stokes equations. And this is a very well-known problem. Many of you might have seen it in your basic engineering courses. It's called the Taylor-Green vortex. And what I'm showing you here is, again, the vorticity after the flow has evolved. So you can see that there are these vortex tubes and so on, and vorticity is concentrated along them. And what you probably don't see is that these are three realizations of a flow, of the same flow, with very, very tiny little perturbations. Remember, these are chaotic problems. So there are two issues here, and you can see that they don't, if you look closely, these things don't really resemble each other. For instance, just focus here, it's very different here, it's very different here, right? So there are very, very big differences here. So there are two issues here. So we are in 3D, but we have a very complex multi-scale problem with lots of small scale, lots of information across scales and so on. So that's the first step. The second step is that it's a very chaotic system. Slight changes leads to different realizations of the flow. Now, if I use all the architectures that I've told you before, all the machine learning, neural operators before, and in fact, I even combine the two sort of leading ones, which is this Fourier and convolutional, local and non-local together, then this is what I get for the same realization. So first of all, and this is state of the art for the previous problems, but when I try to take them into more complex problems, then you see that it completely fails. So you're not even able to resemble flow at all. What you get are some large-scale features, and you don't get any variation. There's no chaos here. Essentially, these guys are chaos blind. So when you apply them sort of just like that, then it simply does not work. So 3D, complex problems, chaotic systems, multi-scale problems, this is not good enough. So what do we have is, more recently, and not just from my lab, but also in the community, people have realized that you can repurpose some state-of-the-art AI to this end, and that is generative AI, right? So all of you have seen Zora, for instance, where videos are generated at scale, DALL-E, and so on. So what is underlying there are diffusion models. Diffusion models, I'll explain a little bit because I have the time, and this is what we repurpose for this multi-scale statistical computation. So remember that this is my problem. So I have some initial conditions, some distribution on the space of initial conditions, slight changes here, but the output changes a lot. So the output distribution is going to be quite wide. And if I just used my previous neural operators, then you don't get any variance. You just get an approximation for the mean flow, and you don't get any small scales. So what we repurposed is the following, that we're going to use a diffusion model. A diffusion model, what it does is essentially the two stages. One is what is called noising. So you start, so this is some data that you have. Initial conditions, flow at a later time. And then what you do is you add noise. So you keep on noising it, till it becomes essentially Gaussian, white noise. Not white noise, but Gaussian noise. So this is what it becomes. This can be done, for instance, by using a stochastic differential equation. So you keep on adding noise, and then you have this noisy thing here. So this is one part of the deal, but the key part of these diffusion models is the reverse step. So where you give it this conditional input, the initial conditions, you give it some noise, and then it will solve what is called a reverse SDE to take out the noise. So it keeps on taking out the noise, till it gives me the solution that I want, right? So this is how diffusion models work, that they add noise iteratively during training, and then they try to take out the noise, and at inference, you sort of use this mechanism in order to take out noise. So what is the training procedure here? So given my initial conditions or some solution at an earlier time, and given this noisy sample, then what this is trained to do is to extract the right sample, the noise-free sample, right? And then you put this into your reverse SDE, and you get this solution. So at inference, I give it the initial conditions, I give it some Gaussian noise, and it returns to me this object here. So this is the basic principle. Of course, we have to adapt it because we are working in 3D, we're working with operators or with fields rather than with vectors. But these are relatively straightforward extensions. And what happens if you do this is the following. So remember that this was my ground truth, vorticity. This was what I got with my state-of-the-art neural networks. Didn't work. But now with these diffusion models, which are actually modeled on the same network, so as you can see, this is some sort of a vision transformer, similar spirit to what I just described, and then you start getting some realizations. These are chaotic flows. So you get some realizations here, best seen through the vorticity. So you can see that the same structure that was there in the ground truth is going to be realized. In fact, it is so good that I have been working on fluid dynamics for a long time. I really couldn't distinguish between the two and say which is true and which is being generated by AI. It really requires a trained eye to do that. And you get the statistical information correctly, particularly the variance, because that's the key quantity, because that measures the distribution somehow. You get the multi-scale information correctly, because this is the ground truth here. the spectrum decays slowly. This is called Mogorov, because there are too many scales in the flow, right? And with the traditional neural network, these decay very, very fast. That's why it doesn't work. Whereas with this architecture here, with this diffusion model, repurposed diffusion model, you get almost a perfect fit. The same with the probability density functions. So you take any point and you try to look at all the realizations. The ground truth is rather spread out, and it beautifully matches what we were able to produce. On the other hand, if you take any sort of neural operator or neural network, then you'll just get a sort of a concentration, a collapse to the mean. And this is also true in all the metrics, particularly for the variance, So you have 5% error, but if you take something which is a neural network, you get about 80% error. So only recently, people have been, including us, have been able to see that how you can scale these approaches to more realistic problems, like three-dimensional fluid dynamics. And this is already enough to do some real-world flows. For instance, a very common flow in engineering is a nozzle. So you just pump air or smoke out, and this is what the realization looks like. This is what a state-of-the-art neural network gives you. It cannot give you these whirls and eddies and so on. GenCFT can provide you that. This is a shock wave, essentially an explosion, a blast, and you can see very nicely that not only is the shock wave approximated, but you get this turbulence behind it, and this is an atmospheric flow. And this is updrafts and downdrafts, turbulent motion in the ground, convection, dry convection, and you can see again that we were able to approximate it quite well. And the whole point of this algorithms is, for instance, this flow here was generated with OpenLB, I think one of your benchmarks, and it took 3.5 hours at this resolution on Alps, essentially. With GenCFT, the same guy, the same inference can be done in 2 seconds. So this is the promise of AI methods. If you're able to make them accurate, they're extremely fast. And then you can do sort of uncertainty quantification at scale, design at scale, inverse problems at scale, and so on. So what about the use cases? So as you can see, the tsunami simulation, which could have taken an hour on a traditional computing paradigm, numerical method, takes about 1 millisecond because it's 2D, it's a small network, and it really matches. So this is our worst sample at this particular buoy location, and you can see that even the worst sample does a very, very good job. So it's a good match. This is for the car example. Again, this is the predicted shear stress. Earlier, this simulation would take like 10 hours on a cluster. This now takes this is 3D, graph neural networks, a little bit more complex, and it still takes 1/10 or 1/100th of a second. So extremely scalable, extremely fast, and so on. So these are all success stories that I've just showed you, but what I have hidden is the caveat, right? There is a caveat here. There are always caveats. And the main caveat is data. Right? So these methods, they work well if you provide them data. This is the reality of machine learning, right? You need lots and lots of data. Just to give you an example, even for the 2D problem, the Navier-Stokes example, so we have CNO, convolutional neural network, we have FNO, all of them scale. In fact, there is even some theorem saying that they are going to scale. As you give more data, the error is smaller and smaller, but the amount of data that you need to get 1% error is just a lot. For instance, with CNO, it's approximately 10,000 samples. And in fact, all these models that I've showed you, for instance, this has been done with 10,000 samples. The diffusion models have been trained with anywhere between 3,000 to 10,000 samples. So there's been a huge amount of data that has been first generated, for instance, on Alps, and then has been used to train these machines. That's why it's trained these neural networks. And this is not possible in every single application, right? There are many, many use cases where you simply don't have that kind of data. And if you have the compute for the data, you can as well solve the problem. So what do we do in that case, right? And in fact, we can take some inspiration from how modern AI systems work, because at the end of the day, these systems are what are called foundation models. So they are not trained on one particular data type or one particular data modality. For instance, if you have a big large language model, it is not just trained on text that comes out of research papers, right? It's trained on all kinds of text with a very, very complex distribution. And multimodal models these days are trained with images, with speech, with signals, and whatnot. All this diverse data is fed into a big model, a foundation model, GPT, for instance. And then for specific tasks, for instance, object recognition or question answering or whatever, image captioning, this is adapted or fine-tuned or prompted these days to get to what is there. So the main point is that there is a two-step process here. First, you take all the data that is out there, which is very diverse, and then you try to process it in some big model, and then try to fine-tune this model to some specific tasks that you have in mind. Now, can we do this for physics, right? This is well and good for language, because language, after all, has some conservative distribution. Now, physics, as I describe it here, is a mathematical abstraction, of course, is in terms of different kinds of PDEs. Different physical systems are modeled by different kinds of PDEs. So you can imagine Poisson equation, modeling, let's say, mechanics, elasticity. You have the heat equation modeling heat flow. You have the wave equation, Navier-Stokes equation, and so on. And for each of these equations, you have infinitely many operators. When you change the initial conditions, you change the boundary conditions, and so on. You have different kinds of operators. So it's a very, very, very rich data set if you want to think about it. So a foundation model in this case, you take some of these PDEs. You can't take all of them because you don't know all of them to start with. And then you train a few operators for each of these PDEs and put them into the foundation model. So that's the first step. It's like what we did before with language and signals and so on. And then once you have that, for a specific task, for instance, you take the wave equation and you take a particular set of initial boundary conditions, you can take this foundation model and adapt it with a few samples. So this is sort of the basic two-step procedure. And it sort of looks very appealing, right? Except that essentially physics is not the same as language. The distributions are very, very different from each other. As I said, if I speak and how sound waves propagate in this room, which is wave equation essentially, is very, very different from what will happen if I start a fire and the fire spreads in this room. Right? That would be more like a heat equation. So these are very, very different kinds of physics. So one sort of a cartoon is different kinds of physics or different PDEs. These are these silos which are sort of disconnected from each other. And what information will I get if I train on two of them or on the third one, which is completely different, right? So feasibility is what is a doubt in the very beginning. If you read a textbook, this is what you would say, that why should sort of learning anything on a small set of PDEs and with certain fixed data distributions allow us to learn something on totally unseen and unrelated PDEs? I mean, this is sort of the basic point here. But unless until we try it out, we'll never find out, right? So the first attempt is to just try it out and see what happens. And this led to a model called Poseidon. So this is Poseidon, the Greek god of nature, essentially. Earthquakes, storms, waves, and so on. And what Poseidon does is exactly this. Means the code is out there, the model is out there. Please have a look at it if you want to. So this is from students of mine, Max Harake. Many of these students have actually come to the CSCS USI summer school. And they have really profited from that. So this is something I'm sure that they would appreciate, or they have appreciated this. So as I said, this is pre-trained on some PDEs, and then it is going to be fine-tuned, hopefully leading to some benefits, right? So this is the basic idea. And the model underlying it, because all these foundation models, you have to have an ML model, right? And this ML model is precisely the transformer that I described to you before, this vision or this wind transformer. So there is a model, what we need is data, then we pre-train, and then we fine-tune. So the data, this is a small-scale experiment, right? You'll see the size of the scale. The data is from fluid dynamics in 2D. This is a 2D model so far. I'll have some 3D results at the end. So it's a 2D model. It takes Navier-Stokes, it takes compressible Euler, shock waves, and so on. And then we build up a data set. Not a lot of images. It's 5 million images, comparable to ImageNet. It's not that small. But this is because of some novel data augmentation procedure that we have. And the largest model that we have released has 630 million parameters. It's way off from some of the large models that even today, I think, Emanuel Schlag is going to talk about a 70 billion parameter model. So we are sort of 2 orders of magnitude off there, right? And also in terms of data, but it's a small scale experiment. And the model itself, the released model, was trained locally on our cluster at ETH. And this took about a week on 8 NVIDIA GPUs. Nothing fancy, because it was small scale. And so how do we test it? So we trained it on essentially the fluid equations, Navier-Stokes equation, compressible Euler equations. And we tested it with those equations and with other equations. For instance, the wave equation, which has not been seen during pre-training, or we added, let's say, transport or forcing, not seen during pre-training. And then we even have things like Poisson equation, Helmholtz equation. None of these have been seen during pre-training. The whole point is this even feasible, that you can train on certain physics and then whether it can generalize to different physics? And the answer is through this fine-tuning, which is, essentially what we do is that we have some latent space and we have some way to reach this latent space. And this is the information, this is where the physics is learned and which is transferred into these models. Now, we have results. We have very good results, but I'm not going to show you there are like 15 downstream tasks, so I'm not going to show you 15 sets of figures. Yeah, I will finish. I'm rather close. Okay, I'm not going to show you 15 sets of figures. What is important is how they scale, right? I mean, this is the whole point. As I increase the amount of data, how does the error decrease? Again, I'm not going to show you 15 sets of these plots either. So what I'm going to do is I'm going to give you two metrics, which are very, very important. And let me try to explain them in a minute. Well, the first metric is, you look at some baseline. This is going to be the Fourier neural operator, which is the most widely used algorithm in some sense in this context. We see, for instance, that 1,024 samples, what is the error on a certain task? So you have 1,024 samples. Then I ask myself, with my model, how few samples can I get the same amount of error? For instance, in this case, it's with 32 samples. So I gain an efficiency of 32, right? I need 32 times less data than I would have done if I would have not done my foundation model. Similarly, you can say that you fix the number of samples, 128, and see how much the error decreases, right? So this is along the y-axis. This feature here is along the x-axis. Either the model is more accurate for the same number of samples, or it requires much less samples to get the same amount of accuracy. So these are the two metrics that I'm going to present. And this is the main table from the paper. Again, a lot of information. So I cut the chase and come straight to the summary. So the summary is across these 15 tasks. It's an average. Essentially not, here is the median, and here is the mean in this particular case. So what you see from this picture is that these models, at least at this scale, work quite well. And I gain sample efficiency by a factor of 50 with the large model. What it means is that earlier, if I had 1,000 samples to get a certain amount of error, I can do this with 20 samples. And you will all believe me that 20 samples is much better and easier to collect than 1,000 samples. And we would like to get this number down even further, right? With ChatGPT, it's essentially a couple of prompts and then you're done. We are nowhere close to that yet. But 20 samples is if it scales, it's already quite a good result. The second thing is that these models, they scale very nicely. So as I increase the model size, you can see that both the metrics, things increase. So as you have bigger and bigger models, they also scale with data set size. So as you have more pre-training data, you'll get better and better results. This is the best model that is out there at the moment. But what is very interesting is that it matters what the model architecture is. Because the green bar here and the purple one here, these are very similar to each other in model size. One is 150 million and the other is 110 million. But they have a different backbone. So this is convolutions, this is transformers. So they've been trained on exactly the same data. They've been evaluated on exactly the same data. But one of them does much better. Because transformers are simply better at getting and accumulating different sources of information. So this is an interesting point. So this tells us quite well that at least it's a feasible concept. We can get sample efficiency or the number of samples down if you have good foundation models. And why does it work? Let me give you an example just because I have a couple of minutes. So this example is the Poisson equation. Remember, it's a very simple PDE that you might have seen during your education. So the input is this forcing term, just Gaussians, and then all that the output does, the operator does, is to diffuse them out, right? Simple. However, there are two things here. The foundation model has not seen it at all. It's only trained on fluid dynamics data, so it has only seen fluid flows. This is not a fluid flow. Fluids don't flow like that. They move, right? And so this is the first thing. There are many other features. So for a machine learning model, this is hard, particularly for a foundation model that has not been trained in it. So now what we do is we start changing the number of fine-tuning samples. So we have a pre-trained model. We change the number of fine-tuning samples. Please focus on this line here. So what you would imagine is that even with one sample, or it will do some sort of fluid behavior, right? Because it's, after all, it's been trained on fluid mechanics. Very quickly, even with one sample, it doesn't provide you fluid flow. It provides you some sort of basic notion of diffusion. When you have 16 samples, it's already learned the basic mechanism of diffusion. And then, as you have more samples, it sort of improves on it, right? So this is sort of the idea, that there is rich physics already in the fluid equations that has been leveraged to solve this problem. And that's why these foundation models are feasible. And the inference time, even the big model, is like 4 milliseconds. And on ALPS, this is on RTX 4090, on ALPS, on the Grace Hoppers, this is less than a millisecond. So this is very, very fast in terms of inference. And you know that data generation takes several orders of magnitude more time. So essentially what we showed is that instead of being this sort of disconnected silos, there's a lot of common physics that goes on, or the language of physics has much more richer representations than we're believed to be. And by pre-training on some of them, we can, with a few samples, fine-tune to different tasks. And this is the main point somehow. It's already being used. People are using it for different applications, particularly in fluid flows. You can see this very, very complex flow past complex shapes, and the foundation model really works quite well. And finally, we need to scale it up, right? I told you that the model was small, the data size was small. So what we're doing now is that we are looking at a 2.5 billion parameter model with and also by a much bigger data set size, about 50 times more. It has 3D. It has some of these unstructured inputs with graphs that I showed you. And then also we want this diffusion model type training, right? Because ultimately this complex physics can only be resolved by that. These are some first results. The model has been trained only on fluid equations, and it solves the Poisson equation in 3D quite efficiently. So this is already good news. And here is the role of HPC. This is where things come in. So for instance, we have not done this large pre-training runs, but we have estimated them. So a big, on a 2.5 billion parameter model with the data set size that we're looking at is approximately 500,000 node hours, right? So this is considerable amount of compute. And for large language models, it's much more. So we are not in that regime, but it's still quite a bit of compute, right? And it also requires a lot more engineering once you have larger models than 2.5 billion. But the main challenge for us is that we need data, right? The pre-training model needs data, and data generation requires a lot more compute than actually training the model. And this is where the fact that most codes out there are not on GPUs, are not properly scaled, is a real innovation. And this is where we are sort of bottlenecked. But anyway, I think this gives a challenge for HPC in some sense in this domain. So with that, I more or less end. I wanted to show you some challenges that are there in trying to apply AI in physics. Many of these challenges have been met, particularly on academic problems, and even on large-scale 3D problems. But the biggest issue is sample efficiency, that you need lots of data, easy to collect for language, very hard to collect for physics data sets, except for weather, where we have a lot of data. And then you need foundation models, but training them at scale is a challenge by itself. But at least it's feasible. We have seen this generalization. And once these foundation models, big size foundation models come on stream, I think then we can see that AI can make a difference to do this kind of physical simulations. But till then, the jury is still out. And with that, I stop. And thank you very much for your attention.
Thank you, Sid. So we do have time for one question, maybe two. Okay.
Yeah.
Thank you for the great presentation. You started with an example from geophysics.
Yes.
And let me continue with an example from geophysics. When you model, for example, mantle convection or subduction zones in geophysics, it is often the case that you have you obtain very ill-conditioned sort of numerical models. And this is simply due to the fact that, for example, you have pressure that is in the order of thousands of gigapascals, while you have velocity, which is maybe 1 millimeter per year. And so, oftentimes, even just using a specialized solver is these are very difficult problems to solve, even for specialized solvers. So I'm interested in how you sort of bridge this gap between machine learning libraries that were maybe not built from the ground up for these type of very ill-conditioned problems and sort of the type of stuff that we need to solve when doing research?
Yes, this is a very good question, but to some extent I answered that at least partially with the fluid mechanics examples, right? There was also a very big spectrum, lots of different scales and so on. But your solvers have to produce the data, or you have some data from measurements, or I don't know the exact I know mantle convection, but I think if once you have data, even if this data is at different scales, machine learning models are there which can take care of it, particularly diffusion models. If you don't have diffusion models, I don't know what can do that. If you don't have enough data, which is probably a challenge in what you're saying, this is the question is still unclear, right? Whether a foundation model that has been trained on simpler physics can scale to your application potentially. And it's not impossible. There are some examples of that, but one has to be careful. So the dedicated the domain-specific features can be incorporated. That's not this challenging, but it's not unfeasible, at least, right? But I'm happy to give you some specific advice offline. I sort of see where your problem comes from.
Very much.
Brian said one question. I will
Yes.
take this opportunity to ask mine. So, I'm not going to touch the scientific part because I put myself in trouble. But I will take about the HPC part.
Yes.
So you mentioned in Pittsdine, you had a measurement between Pittsdine and Alps.
Yeah.
And you had the factor 4.
Yeah, something like that.
Yeah,
4 to
something like
5, yeah.
So if I go from Pittsdine to Alps, we have been crossing from P100 to V100 to A100
Yeah.
and to H100.
Yeah.
And I made some simple calculation. I just have, if I really being modest, I'm having a factor of 8 performance at
Yeah.
least, where I can see here that there's a gap in between. So that's.
I'll tell you why there is a gap, because the problems are memory bounded and not just compute bounded, right? So the memory throughput is what, if you had a slightly lower resolution, like 512 or even 768, then the speed up is enormous on, so it's really the memory, you know? So once you are at 1024 cubed and you have several variables, it does not fit into a single GPU, right? And it does not fit in, and then this is where the gap is.
That makes
So
sense.
so it's.
You still believe that it's inexpensive. So where is this threshold that you believe it should be an acceptable solution, not being tagged as expensive?
It depends. Means I wouldn't say it that way. Means, you know, if you want to do uncertainty quantification, 1,000 samples is what gives me 25,000 node hours, right? And that is, to me, 1,000 samples is not statistically rich enough to do the kind of job that I want to do. So if you give me a certain fixed number of node hours, I want to solve a more complex problem. So this is where I would take it from that perspective. But now if you give me 1,000 samples, I can train my machine learning model, and then I can do uncertainty quantification with 1,000,000 samples. Then it changes the game, right? So I do agree that there is, eventually these systems are going to be, if you can scale your code there, means just imagine the amount of code that is out there which has been on old CPU systems with Fortran and whatnot, and people are working on that, certainly, but I think the ambition increases, right? So you have fixed amount of compute, you don't want to solve the same problem faster, you want to solve bigger problems. And then I think there, from that perspective, we are still constrained.
Sid Mishra, everyone.
Thank you very much.
Thank you.